In this video, we're going to start looking at the rules of differentiation. Our starting point will be straight lines because we already have some knowledge of the gradient of straight lines. So suppose we have the line y equals 7x. We know from previous study of straight line graphs that the gradient of such a line is 7. And since the gradient is the same at all points on the line, the gradient function is also equal to 7. We can also calculate the gradients of horizontal lines. For example, if we have the function f of x equals 9 and we graph y equals f of x, we get a horizontal line. And as it's a horizontal line, it has a steepness of 0 and therefore a gradient of 0, which means the gradient function here is f dash of x equals 0. Before we move on, let's just examine the notation we've used here. So if we have a function defined as y equals something, we write the gradient function as dy dx. Here we're using Leibniz notation. And if we start with a function defined using f of x notation, we write the gradient function as f dash of x using Lagrange notation. So the way you write your gradient function will depend on how your original function has been written. Let's now explore the gradient function for a curve. We'll start with y equals x squared. The way I'd like to do this initially is we'll calculate the gradient at several points on the curve and we'll see if we can spot a pattern. Let's start at the point x equals 1. We could draw a tangent at this point and we could calculate the gradient of this tangent. For every 1 unit that we move in the positive x direction, we're moving 2 units in the positive y direction. So the gradient of the tangent at this point is 2, and therefore dy dx equals 2. Next we'll do x equals 2. We'll draw another tangent. And then here for every 1 unit we move across, we're moving 4 units up. And so at x equals 2, dy dx would be 4. Next we'll do x equals 3. We need to zoom out a bit for this. Again we draw the tangent. And here, for every 1 unit we move across, we'll move 6 units up. We'll just zoom in a bit to see that a bit more clearly. 1, 2, 3, 4, 5, 6. So the gradient at the point y equals 3 is 6. Let's move down on our curve a little bit and do 0 next. So at x equals 0, if we draw a tangent, we end up with a horizontal line. And that tells us at x equals 0, dy dx equals 0. Let's try some negative values. Here's a tangent drawn at -1. This time we can see for every unit we move in the positive x direction, we move 2 units downwards. That tells us we have a gradient of -2. So at x equals -1, dy dx equals -2. If we draw a tangent at x equals -2, we can see there's a gradient of -4. And finally, if we do -3, we can see there is a gradient of -6. And now let's just run an animation between -3 and 3 to show that the gradient actually takes all of the values in between on its way through those points. And so if we look at the values in the table, you may have spotted that the derivative of the curve y equals x squared is dy dx equals 2x. Now this isn't a proof, this is just spotting patterns. And part of this unit will be learning how to prove the gradient of functions like this. But for now, I'm just going to introduce you to a rule for differentiating terms of the form x to the power of n. And once we've practiced using this for a while, we'll come back and look at a detailed proof for how it works. So the rule for differentiating a term of the form x to the power of n is we first multiply by the power, so we get n, and then we subtract 1 from the power, so we get n x to the n minus 1. Now at this point in the unit, I'm not going to offer you any formal proof for why this is so, but later in the unit, we'll be exploring something called differentiation from first principles, which will show you how you can derive this rule for certain values of n. Let's just do a quick example though. Suppose we have y equals x cubed. To find dy dx, we multiply by the power, that gives us 3. Then we subtract 1 from the power and get x squared. So dy dx is 3x squared. As simple as that. And this gradient function represents the gradient at any point along that curve. So here is part of the curve y equals x cubed. Suppose we wanted to calculate the gradient at the point x equals 2. Now that we have the gradient function, it's simply a case of substituting x equals 2 into the gradient function. So dy dx at x equals 2 will be 3 times 2 squared, which gives us 12. Represented graphically, if we mark 2 on our graph, we would have a tangent line that had a gradient of 12. And so what we'll do now is a few examples of calculating the derivatives for simple functions. In our first example, we're going to differentiate y equals x to the power of 5. The first thing we're going to do is write down dy by dx equals. So we're stating what we're going to find. And to find the derivative, we first of all multiply by the power, that gives us a 5, and then we subtract 1 from the power, which gives us x to the power of 4. So our answer is 5x to the power of 4. In part B, we have f of x equals x to the minus 2, and we need to find f dash of x. And so this time we start by writing f dash of x equals. Notice the difference in notation between part A and part B. If we have y equals something and we want to differentiate, we would usually use Leibniz notation and write it as dy dx equals. But if we've got f of x and we're asked to differentiate that, we would normally write it as f dash of x equals. So try and be consistent with your notation based on what the question starts as. So to differentiate this function, the power is negative 2, so we'll multiply by the power. And then we'll subtract 1 from the power, which gives us x to the power of negative 3. Now you could stop there, that will be fine for your final answer. But as we progress further through this unit, you'll often find it useful to manipulate expressions of this form. And so, for example, we may choose to write this as minus 2 over x cubed. Now, if you were differentiating something in the exam and you're not asked to, there's no reason to go past this line of working out. You could leave it as minus 2 x to the minus 3. But at this stage, I think it's worth practicing rewriting things in this form so that you get more comfortable doing so, which will help you in some of the more challenging questions. In part C, it says d by dx of x to the power of a third. Where we see d by dx, that is just an instruction to differentiate whatever comes after it. So this question is saying differentiate x to the power of a third. As we don't have y equals or f of x equals, we won't be using dy dx or f dash x, we simply write the answer. So to differentiate x to the power 1/3, we get 1/3 by multiplying by the power. Subtracting 1 from a third gives us negative 2/3. So we get x to the power negative 2/3. Once again, we could stop there if we wanted, but I'm just going to manipulate it into a different form. We have a 3 on the bottom of the fraction, so we could have 1 over 3. And then if we want to rewrite x to the negative 2/3, we could write it as x to the power of positive 2/3 if we put it on the denominator. So there are a few examples of how to differentiate simple functions, and also how we might manipulate them after we've differentiated. The first line of working out in each case is the actual differentiation, and the second line is just an optional step that I've put in, which you'll find comes in handy when we start to progress further through this unit. Okay, here's a few questions for you to have a go at for yourself then. Pause the video and then come back and check your solutions against mine. Welcome back, here are my solutions. Pay particular attention to the left hand side, make sure you're developing good habits for using the correct notation. Part A, dy dx, B, f dash x, and then for part C, if you're just differentiating, you can just write the answer. If you got any of them wrong, I'm going to go through my answers now. So in part A, we're differentiating y equals x to the power of 7. So we're going to write dy dx equals, we're going to multiply by the power, that gives us 7. Subtracting 1 from the power gives us x to the power 6. For part B, we have f of x equals x to the 7/5. So we're going to find f dash of x. Multiplying by the power gives us a 7/5. And then subtracting 1 from 7/5 gets us to 2/5. So we get x to the power of 2/5. In part C, we have to differentiate x to the negative 4. Multiplying by the power gives us negative 4, and subtracting 1 from the power gives us x to the negative 5. We could also rewrite this as negative 4 over x to the power of positive 5.